Okay, anybody else? Just making sure because I did something. Can you guys hear me?
Yeah.
Okay, great, thank you. Okay, we're gonna try going with using OneNote, see if it does a little better. PowerPoint has been really struggling to keep up with the stylus, as I'm sure you've noticed. It starts off okay, and then it's just kind of, as the file builds, it just doesn't really handle it well. So we'll see how this program handles it. Starts off well, but I've never used it before in a really long for a long period of time. So hopefully it'll do okay. All right. Anyway, yesterday we left off with chapter 3, section 2, and we were looking at zeros of a polynomial. So let's look at where we were at. This is what's really important. We were looking at. Um, So we're looking at graphs of polynomials. We were looking at end behavior. So we covered all that yesterday. End behavior. So this is really the shot that really described end behavior. So we're going to be looking at very well, all kinds of polynomials, but in particular when we have a polynomial that has a very large degree, um, we need to focus on just the degree of the polynomial. The term with the largest degree, the largest exponent, will dominate the outcome of the polynomial for very large numbers, right? Only for very large numbers. And so this tells us end behavior. We covered that. Where's the other zeros? Here, this is what I want to look at. Okay, so then we started looking at these statements, the zeros of a polynomial. For some people, the language of the zeros of polynomial might be new, but we use it quite a bit, so it's important to get comfortable with it. This slide indicated that all four of these terms mean the same thing. The zero of a polynomial is the x-intercept point of the graph. It means that when the variable, the input is replaced with a c, when we evaluate the polynomial at c, that the output is 0. And also that x minus c is a factor of p of x. So we'll see why this is in more detail today or in a little bit. But all four of these things are true. So then we explored this polynomial, we factor it, we see that the number 2, if we replace this value here with a 2, like if we evaluate this polynomial, let's put it in blue, p of, and then let's input a 2, we got two options. We can either go to this polynomial, which is blank squared plus blank minus 6, right? And that blank is a 2. So we just plug it in there. Or because we knew that this factored into this equals this, it means that we can also evaluate this polynomial by using the factored form. Two goes into there, 2 goes into there. Okay, so now here, we could multiply this. That's going to be 4 plus 2 makes it 6 minus 6. Okay, that's 0. Or here, we can more quickly, hopefully, easily tell that 2 minus 2 is going to be 0. And then it doesn't really matter what that is, because we'll end up with 0 times something, so I know that the whole thing will equal to 0. Right? Equals 0. Got it? Okay, so that's why when it's in a factored form, it's very easy to tell which values will produce a 0 as an output. I can easily tell that 2 does that, and I can easily tell that negative 3 is going to do the same thing. Good? Whereas when we look at this, it's hard to tell that. If I just give you this polynomial and ask you to figure out when does this thing equal 0, it's kind of hard to tell, right? Not so easy to tell how we can evaluate this, what values of x would produce a 0. So that's one of the great properties of factoring it this way. Good. Okay, and so that's what definition 2 over here of what is a 0. When we evaluate the polynomial at that number, the output is 0. It means that that is a 0 of the polynomial. right? So we would say 2 is a 0 of this polynomial. We would also say that negative 3 is a 0 of this polynomial. Good? Good. Okay, so moving on. Okay, we looked at the intermediate value theorem. If we have a polynomial function, remember graphs of polynomial functions, we were told without really any proof, but you know, you gotta, some things you just can't, you can't prove every little thing in math. There's just so much stuff. We do our best to justify things as best as possible. Not enough, I think. If your approach to math is let me just memorize everything without really questioning it, I think it gets kind of hard because there's just so much stuff. So you have to really try and understand where it comes from. But there's a limit. There's some stuff it's just too much. So this is one of those things that's presented to you without any real proof. You just have to believe me. The graph of any polynomial function, right? Any polynomial is anything that fits the form p of x equals to n x to the n plus, a sub n, a sub n minus 1 x to the n minus 1 plus dot, right? Anything that fits this standard polynomial form, when we look for its graph is going to be something smooth and continuous. It'll wiggle up and down, up and down, up and down, up and down, right? So how many wiggles it produces varies. How often it goes through the x-axis varies. Whether as we go toward infinity this heads down this way, or maybe over here it'll go up that way, right? So it might go up that way toward infinity, or maybe it'll go down this way toward infinity, or maybe it'll over here, maybe it'll go that way for infinity, and maybe this way it'll go that way for infinity, right? Who knows? So it varies, but they're smooth and continuous. The one thing you will never find for a polynomial is that as we graph the polynomial and goes up and down, it will never do this sort of a sharp corner. Never. It will never have a hole in it like that. No holes, no sharp corners. It will never jump like here and then all of a sudden it jumps to here and goes someplace else, right? These are not graphs of polynomials in red. Right? So this is not a polynomial. Not the graph of a polynomial. Any questions about this? No? Sounds good? Maybe? Believe me? Good. Okay. Given that we're dealing with a polynomial, we know that the graph is going to be smooth and continuous, no sharp corners, no holes, it will never jump. Knowing that we're dealing with the graph of a polynomial, this statement says that if we know that there is one point A such that P of A is the opposite sign of P of B, right? So remember, P of A is an output value, P of B is an output value of our polynomial. So there exists a point where the function is positive and the other one, and another point where it's negative, or the other way around, right? We don't know which is which, it doesn't matter. One of them is positive, the other one is negative, right? So this statement says that there must be at least one value C between A and B such that P of C equals to 0. So we looked at this graphic here, and we saw that it's a nice graphic for it. So here's a nice example. A is a possible value of x, B is a possible value of x. So this statement says that if we know for a fact that P of A is definitely negative, and we definitely know that P of B, this is P of B, in fact let's put the point B comma P of B, and this one is definitely a positive value, they're opposite signs. P of A, P of B are opposite signs. And according to the theorem, there must be at least one point C somewhere between A and B such that the function equals to C. Good. There might be more than one. This theorem doesn't guarantee that there's only one. There might be more than one. Right? So maybe if we knew it looked like this, we knew that here was P of A, say that this was the way it was. Here is A, and so therefore this is P of A, right there. And then let's say we have another point over here, B, where we know that down here is P of B. P of B is way down here. Okay, so we have a case where we know 2 points and they are opposite signs. They're both on the graph, so this theorem guarantees that there must be at least one place where it crosses the x-axis. At least one. Maybe the graph looks like that, right? Or maybe the graph crosses it twice, 3 times, maybe like that. 1, 2, 3. Good. Maybe it does this. Maybe it crosses it and then comes back up and maybe just barely touches it and then comes back down. So there could be 2 places where it touches it. Good. Okay, but what it cannot do, the only thing it cannot do is somehow stay positive, and somehow all of a sudden it's over here and now it's negative, because then it would have broken one of our rules of graphs of polynomials, right? Because how did it do that? Was there a hole? Well, we can't have holes. It's a polynomial. Or did it have a break in it, right? If we had like a break like this, well, you can't do that. It's a polynomial, right? So because it's a polynomial, we're guaranteed it must go through the x-axis at least once, maybe more than once. Are there any questions about that theorem? The intermediate value theorem? No. There's a related theorem we'll look at down the road. But anyway, how is that one important now? It helps us put things together so that we can get a rough estimate of what a graph looks like of a polynomial. When you're given a polynomial and you're asked to do a rough sketch of it, the first thing you should do is factor the whole thing out. And that on its own can be a lot of work. Then we're going to look for all the zeros. Once it's all factored out, it should be easy to find the zeros. Then we have the test points, various test points in the region, right? So the zeros are going to partition our horizontal line, our domain, into different segments. And now you got to test each point to see whether the function is positive or negative at those points. So here is our number. Let's say we had the polynomial p of x equals 2. And once you've already factored the whole thing out, maybe it factors into this. Right? Maybe it factors into that. Okay, so then when we look for our zeros, I can tell that one of those zeros is going to be a positive 3, another 0 is going to be a negative 2. I'm sorry, a positive 3 and a negative 2. Okay, so then that means it breaks up the number line into 3 zones. Zone number 1 over here, zone number 2 over here, zone number 3 over there. There's 3 different regions. We want to grab a test point from somewhere here. Why? Because of the following reason. We found that these are the zeros, so I know the graph goes through these points here. Good? If I find a test point and I find that the test point is positive, let's say there's a point right there that's positive, and then over here I find a test point and this test point is going to be negative, say that, then I am guaranteed that this is the only place where it crosses through the x-axis. It can't go through another one, because if it went down this way, then there would be other x-intercept points. Right? So we already know the x-intercept points. We can't have any additional x-intercept points. So once we have a test point, all we really care about, besides if you can actually find the ordered pair, that would be nice. But in some cases, the equation is really ugly, and you might just focus on whether it's positive or negative, so that we know whether it goes above the x-axis or below the x-axis. Good. Okay, so find test points, and then use end behavior of your polynomial to put it all together and sketch together a graph. Okay. So here was an example we did. here is a polynomial. We factored all the way. We found the zeros. It broke down the number line into the zone over here, the zone here, the zone here, and the zone there. We come up with test point values in each one of these zones. And we can figure out whether our results are going to be positive or negative in each of those zones. And in this case, I think they're not too difficult, so we can probably just find the answer. Good. So we have probability, not probability, the polynomial is blank times blank minus 3 times blank plus 1. And one of those test points we tried is -2. We plugged it in there. We can also evaluate it at this, right? So that's the same thing. P of this is the same thing as something cubed minus 2 times something squared minus 3 times something. Okay. So we plug in a -3 and we ended up with -8 minus 8 makes it -16. This ends up giving me -10. Or we can evaluate it using this equation, right? So here we evaluated -1/2. So this is going to be -1/2 times, and this is going to be -3.5 as a mixed number. -3.5 as a mixed number, which gives you -7 over 2. -7 over 2. And this is +1/2, which ends up giving me +7 over 8. Good. We can also test the point 1. That should be an easy one. Let's plug in a 1 into here. 1, 1, 1, which would give me 1 times -2. Oh, there's also a 1 over there. 1. 1 times -2 times 2. So P of 1 should be equal to -4. Good. Okay, so we get all those points. We can create a table. There's a nice little table over here somewhere. Nice little table over here, same results that we got. So we have our zeros, we have a few other test points. So these create these ordered pairs right in here that help us begin to think of our shape. We also think about the end behavior. We know that because the leading term, the term with the largest degree is a power of 3, it's +1 x to the third power. That's how we know that it'll go up toward positive infinity, right? We know that y will head towards positive infinity as x heads toward infinity, right? And we also know that it'll head this way. It'll confirm it that it'll head this way, that y will head toward negative infinity as x heads toward negative infinity. I'll give you this. Okay, so putting all those things together helps us find a rough shape for our graph. Any questions about that? I know I ended up recapping a little bit of yesterday's, but I feel like I didn't really do a good job with it. I was having a lot of trouble with PowerPoint. It's frustrating me. Any questions? Maybe. Okay. So the next thing we're going to look at is the shape of the graph near 0. Okay, so in general, if c is a 0 of the polynomial, and the corresponding factor x minus c occurs exactly m times in the factorization of m, then we say that c is a 0 of multiplicity m. Good. We'll see an example in a second. By considering test points on either side of the x-intercept, 0, c, 0, we conclude that the graph crosses the x-axis at c if the multiplicity m is odd, and does not cross the x-axis if it's even. Okay. So let's look at. So there's our screenshot that gives us the general rule. If we have a zero of a polynomial with multiplicity m, then the shape of the graph of p near c follows the following rule. Okay, so this is saying that if we're given some polynomial, p of x equals some big ugly thing, x to the 6th power, 5x to the 4th power, plus dot, 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 some ugly thing. But let's say that after I factor it, the whole thing turns out to look like this. To the 3rd power, x plus 1 to the 2nd power, x minus 5 to the 4th power. I don't know, something like that. Well, let's make it, let's just leave it to the, like that. Okay, so let's say that that's how it factors. It factors like this. This is saying that the zeros are positive 2, negative 1, and positive 5, right? These are the values that will result in the polynomial equaling 0, right? If I replace this x with a 2, all these x's with 2, I will end up with 0 times something, so therefore the whole thing will be 0. But moreover, this is what they mean by multiplicity. This power 3, this guy, and also, well, even if it's not there, by default there's like this little invisible 1 there. 1. This is the multiplicity. Good, the multiplicity. So we'd say that 2 is a 0 of multiplicity 3. 2 is a 0 of multiplicity 3. Good. And we'd say that 2 is a 0 of multiplicity 2. Good. And 5 is a 0 of multiplicity 1. Of multiplicity 1. Okay, and so this theorem is saying that if we have an odd multiplicity for the 0, then the graph is going to punch through to get to the other side of the x-axis, right? The fact that it's a 0, it means that it's a point on the x-axis. So when I graph this one, I know for sure it'll go through the point 2, 0. Right, when I do like a rough sketch of this graph, here's this, I know for a fact that the point 2, 0 is going to be on my graph. I know that the point -1 and the point 5, so here's 5, here's -1. So here's -1, here's 2, here's 5. Because these are the zeros, I definitely know that these 3 are the places where my graph crosses the x-axis. These are definitely 3 points on my graph. This is saying that because the multiplicity is odd at 2, it means that my graph will either come from this direction and punch through to the other side, or maybe it'll come from this direction and punch through to the other side, okay, because it's odd. Because the multiplicity, wait, what did I do with, oh, this is a mistake? Oh, this should be -1. Nobody said anything. This right here should be a -1. -1 is a 0 of multiplicity 2. Okay, so multiplicity 2 is even, which means that it'll do one of these things. So I'm guaranteed that when I see the graph of this, either it'll come down, touch it, and then come back up like a happy face, or maybe the other way around. It'll come from this direction, touch it, and then go back down the way it came. Good. It will not punch through to the other side. So the odd multiplicities punch through to the other side, and the even multiplicities just touch it and go back the way they came. Right? At this point, we don't really have a way of knowing whether it's going to be this shape or this shape. We just know it's one of those two shapes when we have an even multiplicity, and we know that it punches through to the other side when we have an odd multiplicity. Good. So again, it's just another little piece of the puzzle that helps us figure out what the graph of the polynomial is going to be. Let's explore that with Desmos for this thing. P of x equals, and then we had x minus 2 power of 3 x minus 1 plus 1 goes to the power of 2 and x minus 5 and an extra to the power of 1. Okay, so here's what the graph looks like. Zoom out a little bit. Comes down, goes up, comes back down, does this thing. Okay, but we're just focusing on what's happening around the x-axis, the graph near its the x-axis. So here are the three zeros, right? It goes through the point -1, 0 because of this thing. It goes through the point 5, 0 because of this thing, and it goes through the point 2, 0 because of this guy. Okay, and then the 2 is a 0 of multiplicity 3, which is an odd one. That means it punches through it. See how the graph comes through on one side and punches through to the other side? Good. Same thing with this one. It has a multiplicity 1, which is an odd power. So it punches through to the other side. It comes through and punches through to the other side. Whereas here, the multiplicity was 2, that's even. So it comes down and just touches that x-axis and goes back up. Right? So that's helping us with the behavior of our function near the x-axis based on the multiplicities of the polynomial. Good. If I change this to be some even power, like let's say 4, see how it changes this? Now it's an even power, so now it doesn't punch through to the other side. If I change it to 3, it's going to punch through now. Comes through and goes right through the whole thing. So if I change it to a power 7, it's going to go through the whole thing. Right? Obviously, the whole rest of the graph changes, but right now we're just focusing on what happens with these guys, and it's doing a pretty good job of that. But so if I put a 2 on there, then it comes through, touches, and goes back up. Right? Same thing with this one. At -1, we have an even one. That means that right now it's coming up, touching it, and coming back down. If I change this to a 2, see that's going to do that for all of them. Comes down, touches, comes down, touches, comes down, touches. Good. If I put a -1 out in front, and it's going to flip the whole thing upside down. But still, it keeps the same property that it comes through, touches, and comes back down the way it came from, because right now I have the multiplicities all even. Any questions? No? No? Okay, so now let's look at this thing and do like a rough sketch, putting together the things we know. Let's see, first of all, the zeros. That's going to be easy. Let's put a little table, and we'll put zeros, and the multiplicity. So of course, 0 is going to be one of the zeros because of this 0, and it's got multiplicity 4, and then +2 is another 0, and it's got multiplicity 3, and -1 is another 0, and it's got multiplicity 2. Okay, so because these are zeros, that means that I have ordered pairs. I already have these ordered pairs in our graph. So I already have 3 dots in my graph. The point 0, 0, the point 2, 0, and the point -1, 0. Good. On my number line, as I begin to kind of sketch what this is, I'm starting to get a nice idea of what this graph is. I'll use this. Here's the y, here's the x. Okay, so far I have the point 0, 0, and I have the point 2, 0, and I have the point -1, 0. So those are the 3 points I have so far. This breaks up our number line into 1 zone, 2 zones, 3 zones, 4 zones. So I need some test points so that I can figure out what the graph is doing in each one of those sections. Right, so this one was -1, 0, and +2. So let's pick a test point. It doesn't matter as long as a nice simple one from each zone. So let's pick from over here, let's pick a -2. From in here, let's pick -1/2. From in here, let's pick 1. And from over here, let's pick 3. Good, so now I have to figure out what each of those values is in order to solve this. Let me make some room here. Like that. Okay. Okay, so I need to figure out a table where I need to figure out -2. Okay, so P of blank equals blank to the power of 4, blank minus 2 to the power of 3, and blank plus 1 to the power of 2. And the first one we want to work with is this -2. -2, so -2, -2, -2. That's going to work out to be a -2 to the power of 4. That's going to be 2, 4, 8, 16, +16, times, and this is going to be -4 to the power of 3. That's going to be -64. And this is going to be -1 to the power of 2. That's just going to be +1. So at the end of the day here, we end up with 16 times, what's 16 times 64? So -1024. But really the most important part is that it's negative. So I know that my graph is way down here somewhere. Somewhere over here is the point -2, -1024. Good. Okay, so now we figure out a point in between here. So -1/2. P of blank equals to blank to the 4th power, blank minus 2 to the 3rd power, blank plus 1 to the 2nd power. Now I'm going to plug in those -1/2s everywhere. -1/2, -1/2, -1/2, -1/2. Okay, and all right, well that's going to be +1, 2 to the power of 4, which is going to be +1/16. This as a mixed number is 7/2, -7/2. Wait, no, 5/2. Right, so 2.5, -2.5, raised to the power of 3. And this is just going to be 1/2 squared, so that's just going to be 1/4. So that's good and ugly. That's going to be 125 over 8 1/16 times 125 to the power of 8 times 1/4. So 16 times 8 times 4 gets you to 512. So 125 divided by 512 is the other ordered pair. Okay, so the actual value isn't even really that valuable here because it's kind of hard to graph it. I mean, it's, I don't know, close to 1/4 when you reduce it. So it's going to be just some dot over here somewhere. So I don't know, maybe around there. That's going to be the point negative 1/2 comma 125 over 512. So we have that point right there. The number 1, if we evaluate this at 1, p of 1 is going to be 1 to the 4th power blank minus 2 to the 3rd power blank plus 1 to the 2nd power. Plug in a 1 here. 1, 1, 1, and a 1. That's going to be equal to 1 times negative 1 to the 3rd power, which is negative 1, and then 2 squared, which is 4. Well, that one was easy. So we end up with negative 4. Finally, an easy one. Okay, good. And then next, p of 3, 3 to the 4th power, blank minus 2 to the 3rd power, blank plus 1 to the 2nd power. And we're going to plug in 3. So 3 in there, 3 in there, 3 in there, and 3 in there. And that gets ugly. 3 to the 3rd power, that's 27. Oh, to the 4th power, that's going to be 81. Times 1 to the 3rd power, that's just 1. And then 4 squared is 16. So it's 81 times 16, 1296. 1296. Good. Okay. All I really care, the most dominant important thing here is that it's a negative value. Here, this is output is negative. Output is negative. So I know that the point is going to be somewhere over here. So I have a point of like 1 comma, I don't know, negative 4 over here. Something like that. 1 comma negative 4. And then over here, the output was positive again. Nice big positive output. So I know that when I graph it, 1296, that's going to be some huge value over here somewhere. Way over here at 3 comma 1296. Good. So we're starting to get a sense of what this graph will look like. And so we can kind of piece it together. And at this point, it is just a guess. But my guess is that it does something that looks like this. Yeah. Like that. No. Okay, that goes that way. Or whatever, you get the idea. It goes up, crosses at this point, has a little curvature there, comes back down this way, comes back up that way, and then goes up that way. Right? And that's just a guess. You might wonder, how do I know that it does just like this little thing comes down here and goes that way? How do I know it doesn't do something like this? How do I know the graph doesn't come down, does like a little bump, 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 hit that guy, come back up here, wiggle, 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 and go that way? Well, we have absolutely no evidence to indicate that it does that. So one guess is as good as the other, but I don't know if you've heard of Murphy's Law. Contrary to any evidence, the simplest explanation is usually the correct answer. So that's sort of what happens here. The simplest thing you could do is just have one little bump there and come back this way. And that's usually the answer. Not always, but usually that's what it does. It just comes up, has one little bump, and comes back that way. Good? Okay, so now let's match it up with everything else we know. How about multiplicities? Does it match what we thought about multiplicities? At 0, multiplicity 4. At 2, multiplicity 3. Negative 1. How did I screw this up? What's happening here? 0, 0. Okay, we have this guy. Multiplicity 4, it's not supposed to go through. So this is wrong. It's supposed to touch it and go back the way it came from, but then how come we have a 1 here? 0, 2, and negative 1. 0, 2, and negative 1. Multiplicity at 0 is 4. Multiplicity at 2 is 3. Okay, so this one matches that it goes through. Multiplicity at negative 1 is also not supposed to go through. Did I mess up with the signs here? Negative 1/2 gives you a positive, gives you a... Oh, how come nobody stopped me? I blame you guys. Hello? There's a negative right here, raised to a power of positive 3, which means that this must be a negative, right? It preserves its sign. Here, this was a 4, so that gets rid of it, makes it positive. And here, this is a square, so it gets rid of the sign. So anyway, this is a negative answer. Good. So going back over here, when we graph this guy, this is supposed to be on the other side. It's supposed to be down here. So let's see if we can erase some things without erasing the whole thing. Let's get rid of that. And let's get rid of that. Okay. So it's supposed to be a point like over here that is negative 125. Let's make it in blue. Right, so that point right there. Okay, now it matches my multiplicity, right? Because multiplicity at negative 1 was even. It's supposed to just kiss it, just touch it, and go back the way it came from. So now it matches that a little bit better. And then at 0, we also have an even multiplicity. So it's going to come up and touch it and go back the way it came. And then it goes this way, touches that thing, and goes up. And 2 is the only one that has an odd multiplicity, so it punches through and gets to the other side to go that way. And now it matches it. Any questions? So far we're okay? And then the last piece of information we have deals with end behavior. So end behavior, to be able to figure out end behavior, I need to figure out the power of the leading term. So really we'd have to expand this whole thing out. However, I don't really need the entire polynomial. I just need to know what's the polynomial with the biggest degree. So we can kind of sort of begin to FOIL it all out. So let's do it this way. Space. Okay, so I have p of x is equal to x to the power of 4, x minus 2 to the power of 3, and then x plus 1 to the power of 2. Okay, if I FOIL this guy out, that's going to be easy. Let's just do that guy. That'll be x squared plus 2x plus 1. So that takes care of this. And then there are these terms. Let me rewrite it as x minus 2 times x minus 2 squared. We know how to expand that. So this will be x to the 4th power. Let me go ahead and expand this. This distributes easily into there. So I'm distributing this into here and this into here. So I'll end up with x to the 5th power minus 2x to the 4th power. And all of that still needs to be multiplied by x minus 2 to the 2nd power times x squared plus 2x plus 1. Okay, and then as I FOIL this, let me FOIL this guy out. That one's not going to be difficult either. This guy by itself is x squared minus 4x plus 4. Right, that's this thing. Don't worry, we're not going to FOIL out the entire thing. I just want to see what the leading term is. And the leading term only cares about the biggest degree. So we'll end up with these guys. Okay. As I begin to FOIL these two out, right, as I'm going in the process of trying to figure these out, I'll start FOILing these. But if I'm just interested in figuring out the biggest term, it's really just going to be this times this. Right? So as I begin to FOIL it all out, I know that I'll get the term x to the 4th power from these. And then from those two, I'll get plus 2x to the 3rd power, right? Plus x squared, right? Minus 4x to the 3rd, minus 8x squared, right? So that's the beginning of this whole FOILing process. All of that still needs to be multiplied by this x to the 5th minus 2x to the 4th power. So when I FOIL this guy out, again, I'll have to multiply this times this, and this times that, and this times that over there. And then later this times this, and this times that, and this times that over there, and dot, 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 dot. But as I begin that FOILing process, the biggest term is going to come by doing this one times that one. So it'll end up being x to the 9th, and then plus 2x to the 8th, plus x to the 7th, right? Dot, 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 dot. So all that really matters for end behavior is to figure out the biggest term. And the biggest term is going to be that guy, x to the 9th power. Good. 2 of those powers come from here. 3 of those powers come from there. And then x to the 4th. So really we could have seen that it's equal to 7, and 2 makes it 9. So it's x to the 9th power. You just have to be careful of what the constant in front is going to be. Now in this case, it was super easy because they're all 1s. There's a 1 there, there's a 1 there, and there's a 1 there. So we just multiply those 3 1s, and then that's how we get that there's a 1 in the hour, in the biggest power. And then we just added 4 and 3 and 2 to give me a 9. Good. So the rest of it, for the purposes of end behavior, doesn't matter. All I have to know is the leading term, and it's a power degree 9, it's odd. So I know that the end behavior is going to match exactly this. So it just helps us confirm that it's going to have this behavior. It's going to follow the same end behavior as x cubed, as it's going to have y go to infinity as x goes toward infinity. And down here, y is going to go toward negative infinity as x goes toward negative infinity. So it's going to match this, right? Because it's a power 9, it'll match the same behavior as x cubed. Remember, x cubed has this sort of shape. Right? So x to the 9th power will be similar. End behavior. Any questions? No? 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 Maybe sort of, kind of? Okay. Let's see what the author did. Okay, so we have 0 multiplicity 4, 2 is a multiplicity 3, negative 1 is a multiplicity 2. Okay, even multiplicities, the polynomial is degree 9 and has a positive leading coefficient, so we know that it's going to follow that behavior of an x cubed. So as y will go to infinity as x goes to infinity, y will go to negative infinity as x goes to negative infinity. Okay, and then similar process that we do, come up with the zeros, figure out a test point, and then from that we can start to stitch together what the graph will look like. Any questions? No. Local maxima and minima, it's going to be, I think we've discussed this before, as we have our graph and we look at all the places where there's like a little bump, either bumps up or bumps down like this, we call these local maximums, local minimums. By definition, it means that there must exist some little region of the domain, some little neighborhood of the domain, where this one is the king of the hill, right? Any other value of x that you choose in this neighborhood, when you evaluate it, it always ends up being less than f of a. That means f of a is the largest value in that little zone. It's not the largest value of our function, because notice, for example, over here, these output values are larger than f of a. But within a little neighborhood, it is the largest value. There exists a little neighborhood, a little subsegment of the domain such that f of a is the largest value. And similar for a local minimum, there exists a little neighborhood, a little section of the domain that contains the value b such that f of b is the smallest value in that neighborhood. It's not the smallest value of our function. As you can see, all these values over here are smaller than f of b, but there exists this little neighborhood such that f of b is smaller than any other point evaluated. Any other value you choose near b and you evaluate the function, you're always going to get that f of b is the smallest in that neighborhood. Good. So visually we can see it. When we graph it, we can easily spot them where the local maximums and local minimums are. But it takes a little bit more work to figure those out when you have an equation and you have to figure out where those little bumps are. Okay. This next theorem here just kind of helps us identify how many to expect. So if p of x is a polynomial, a standard polynomial of degree n, then the graph has at most n minus 1 extrema, combinations of maximums and minimums. And note that this is at most. It doesn't mean that it has to have that many. It means that it's the most it could possibly have, but it might be less. So this is saying that if we have a polynomial given to you of the form p of x equals to x to the 6th power plus 2x to the 5th power plus 3x, for example, this theorem is saying that it has to have at most 5, right? N minus 1, 5 bumps, right? Local max slash local min. But it doesn't have to have that many. Note, for example, that if I have p of x equal to just x to the 3rd power, according to this theorem, there would be at most 2 local maximum, local minimum. But if we think about the graph of it, there are none. Right? When we graph x cubed, it looks like this. So there are no local max or min in x to the 3rd power. Right? So this is saying at most 2. At most 2 local max, local min. That doesn't mean it has to have any at all. That's min. But if I didn't know the graph of this thing, I could definitely tell that there are not 3 maximum minimums, or 4 or 5 or 6. There's at most 2. Any questions?
I have a question.
Yeah.
Have you started posting the PowerPoints with your sketches on it yet?
So I tried to stay with PowerPoint for that reason, but it is not working out for me. PowerPoint doesn't want to keep up with the stylus thing. So I'm not going to be working with that anymore. And so I can try and save this thing, but I don't know how well it'll do in terms of saving it. Do you have OneNote? That's another thing that's not as ubiquitous as PowerPoint. If you if you have OneNote, then you'll be able to save it, but I mean, be able to open it. But if you don't have OneNote, I'm not sure if it'll open. I might be able to save the whole thing as a PDF file, so I'll have to explore that. But we might have issues with that now. Do you have OneNote?
I don't, but okay. Can you keep me updated on what you do?
Okay, sure. I'll try and save it as a PDF file and see if it'll save that whole thing and if it saves the writing part of it. Otherwise, you know, the video is really the only source of the external writing part of it.
Okay, awesome. Thank you.
Okay. Now, as far as the previous ones, I did start saving. I did put the other ones on there. I think up through like the second or third section in chapter 2 is already up. So if you go to our Dropbox, there's one that says PowerPoints, and the other one says something like PowerPoints with instructor notes or something like that, so that you can have both the original one and the one that has all the writing on it. Did you notice that one? And have you been able to open it?
Sorry, what did you say?
On the Dropbox, there's already some of the ones that I've saved that have the writing on it. Have you been able to open those?
Oh, I didn't check Dropbox. I was checking Canvas.
Oh, no. It will definitely be on Dropbox. I really don't put any of this stuff on Canvas.
Okay.
Okay. So awesome. You were able to get the original PowerPoints from Dropbox, right?
Yeah, correct.
Okay, so there's another file on there that says PowerPoints with instructor notes, and I put chapter 1 and some of them from chapter 2 on there. So check those, see if you can open them.
Okay, awesome.
Okay, graph this polynomials and determine how many extrema are in it. Okay, so don't panic. They're not asking us to hand graph all of these things. They're just saying if we graph them, confirm that it satisfies the theorem for local maximum, local extrema. And so from the theorem, because this is the degree of the polynomial is 4, we know that there must be a maximum of 3 local max, local min. And because this has degree 5, there must be a maximum of 4 of them. And because this is a degree of 4, there must be a maximum of 3 local maximums, local minimums. Good? And that's what this statement is saying. And if we graph them, they're already on here, so let's just look at them. See, here is the graph of this polynomial, degree 4, and there is 1 local minimum, 1 local maximum, another local minimum. There are 3 of them. So it satisfies our statement. This is degree 5. There's a maximum of 4, and there is 1, 2, 3, 4. Right? There's actually 4 of them. And then this next one has degree 4, so there should be a maximum of 3, but in fact there's only 1. And that's okay. It's a maximum of 3, not that there has to be 3. Good? Good? Questions? Okay, so that takes care of this section.
It opens, but like without the notes.
Oh, well, in that case, I won't be able to give it to you then. I saved it. It opens for me, but there must be some sort of thing. I don't really know. It's probably that your PowerPoint software is not updated to the most recent version of the software, or that your access to it is limited. You know, like sometimes they have a student version of the PowerPoint versus a professional version of the PowerPoint with certain features available, that kind of thing. It just adds so much complication with all these technology things. So explore why you're not able to save it. If look at the file type. I'm not really sure what the file type that it is. You know, the .ppt or the .pptx or whatever it is at the end. Look that up, Google it, and see what kind of software is needed to open that file, and see if you can get it. I wouldn't spend any money if I were you. I don't think it's worth it. But there might be some free way of either updating your software or maybe finding another software out there that will open it. Maybe opening it through the Google version of PowerPoint. I forgot what it's called. But there's like a Google version of PowerPoint that might open it, and it might open the writing. There's also the Apple version of PowerPoint that might open it. So you know, it just kind of sends you down this rabbit hole of trying to figure out how to open it. But from my end, I've done what I could because I've saved it from my end, and it does have the writing. I can try and save it as a PDF file. I think that might be doable. So I can try that, and you know, PDF files are becoming pretty ubiquitous as the universal sort of software that allows us to exchange information the easiest way. So I can try and save it as a PDF file, and that might solve that issue. Same with this. I'll try and save this stuff as a PDF file now that I've converted over to OneNote. And we'll do our best. But if it doesn't work out, then you'll just be left with the option of watching the video and taking notes on your own.
Yep, awesome. Thank you.
Sorry, I know. Damn Corona. I missed my classroom. Are you guys pretty happy with the online thing? Or do you wish you were back in the classroom setting? People like the online?
I do not like the online school stuff. I learn way better in person.
Cool. Yeah. Well, I teach way better in person too. So there we go. Okay. Any rate, moving on. We're gonna cover section 3.3 of chapter 3, dividing polynomials. This should be a nice review of old things, I hope. Though I find a lot of people tell me that they've skipped division of polynomials in prior classes, so we'll see. But for most of us, I think it's going to be a nice review. How to divide polynomials, and we're going to do it the long way, and then we're going to do this shortcut way called synthetic division. And then we'll look at the remainder and factor theorems that will help us, again, be able to go back and piece together information to get a rough sketch of what the graph of polynomial is. Okay, so dividing polynomials. In this section, we begin the study of polynomials. Okay, so we got to factor polynomials. Let's begin with the long version, the long division of polynomials. And in order to kind of study how we divide polynomials, we should review how we just divide numbers in general. So if we had to divide 38 divided by 7, so if we had to do it the old way, if you remember this, 38 divided by 7 in this style, then maybe we go over to this style, right? And then 7 goes into 3. Nope, it does not. 7 goes into 38. It does go into 38. And it goes into it 5 times. So we put a 5 here. And then we multiply these two together to get a 35. And then we subtract to get a 3. Good. So this is the quotient. And this is the remainder. right? So from this process, we can see that it goes into it 5 whole times, and there's a remainder of 3. So we can go back and represent this fraction, 38 over 7. We can say that this is equal to 5 plus 3/7, right, as an addition. Or we can also just combine them together as a mixed number and say that it's 5 and 3/7 as a mixed number. Good. We're happy with that process? Okay, so same thing. We end up with 38 divided by 7, and then we have our quotient plus, and it's the remainder over the divisor, right? Keep that process in mind. When we want to divide a fraction like this, we get the quotient, which is the whole number part. How many times does this denominator go into that? A whole number of times, 5 times. Okay, so armed with that, we want to expand that out to cases where we have a rational quotient here. We have a polynomial divided by another polynomial. Then when we divide it, there will be a quotient part, a quotient part which will be another polynomial. So it goes into it a whole number of times, this polynomial number of times, plus, and there will be a remainder polynomial divided by the divisor polynomial. Good. Once we have it in this format, then we can multiply both sides of the equal sign by the divisor, and we'll end up with this, divisor times quotient plus the remainder. So that's kind of like this, coming up to this again. We have 38 divided by 7 equals to 5 plus 3/7. We're pretty happy with that. Now what we want to do is multiply everything by 7, and then distribute, of course. And so I'll end up with 38 equals to 7 times 5 plus 3. Good. So 38 equals to, remember the 7 was the divisor. 5 was the quotient. And 3 was the remainder. Good. So the original value that we wanted to divide by the divisor is equal to the divisor times the quotient plus the remainder. Right? It's called the dividend. The dividend is equal to the remainder, the quotient times the divisor plus the remainder, which is this guy right here. Any questions about that so far? Kind of. All right, let's practice. Remember, this is long division. I know some of you guys already know the synthetic division, but we need to practice doing it the long way as well. So let's do it the long way. Okay, we have 6x to the second power minus 26x plus 12, and we want to divide that by x minus 4. So putting it in this style, we know that it's going to be equal to this. This is going to be 6x squared minus 26x plus 12. Okay, so we have to make sure, first of all, that all the powers are represented in a descending order. What I mean by that is that we're making sure, and it's already been satisfied here, but we'll see another case where it's not. So the power is 1 there, and then the next one has to be x to the 0 power or no x. Here, the highest degree is a 2, then there's a 1, and then there's no power. So all the powers are represented in descending order. If one of them is missing, we have to insert it. And we do that by inserting it, but also putting a coefficient of 0 in front of it. Okay. So we'll see an example like that soon. All right, so now what we want to do is match the terms. So the leading terms here, this one right here, just by itself, the x, and this. I want to multiply blank times x so that it equals exactly this, right? And there's different ways of doing this, so if you already have your own way of doing it, that's fine too. But this is just the way I do it. So it's got to be positive 6x times x equals 6x squared. Right? Make them match exactly, including the sign and everything. Then this times minus 4 gives me minus 24x. Good. The next thing I'm going to do is I'm going to distribute a negative 1 and then bring it down, and then add down. Right? So I'm going to distribute this minus through here. That's going to give me a minus 6x, and I have positive 6x squared minus 6x squared. When I add them down, right, I'm going to add these down, then they cancel out because they're opposite signs. That's just the way I think of it. If you just want to think about subtracting them, that's fine too. But I think it takes away some of the confusion that happens in these kinds of cases, right? Because if I just said minus 26 subtract negative 24, that kind of confuses people. So that's why we distribute a minus and then add down. Distributing a minus, I get a plus 24, and then when I add them down, I get a minus 2. Minus 2x. Bring down the next term, which is 12. And then again, I want to match this. Blank times x equals exactly this. So that's how I know it's got to be a minus 2. Minus 2 times x becomes minus 2x. Minus 2 times minus 4 becomes a plus 8. Right? And then again, I distribute a minus 1. And then I add them down. Maybe I should have put the plus in a different color. And then I add them down. So when I distribute a minus, that becomes plus. So minus 2 plus 2, these guys cancel. A minus becomes a minus 8. And when I add them down, that's going to be 12 minus 8 gives me a positive 4. Good. The degree, I know I'm done when the degree of this is less than, strictly less than the degree of this thing. So this has no x, and this has x to the first power. If this had been a case where this was the degree 3 there, and this gets down to x squared, that's how I know I'm done, because this is a degree smaller than this one. If they were both 3, then I would be able to keep going. I can find another way of doing it. But in this case, they're both equal to 1. In this case, they're both, in this case, this has power 1 and this has power 0. So that's how I know I'm done. I found my remainder. Which means that this pollen over here is the quotient. Good. So now I can put it together in the same format as before. This minus 26x plus 12 divided by x minus 4 is equal to 6x minus 2 plus 4 divided by x minus 4. Good. And then if I multiply both sides of the equal sign, some more space here. And if I multiply both sides of the equal sign by that x minus 4, and then distribute, I'll end up with 6x squared minus 26x plus 12 equals to 6x minus 2 times x minus 4 plus 4. Good? Questions, 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 questions? So they get the same answer I got. 6x Times that plus 2, just subtract that, give it 11, 4. Yep, they got the same answer I did. So the original division is equal to this little polynomial that we got as our quotient plus 4 over x minus 4. If we multiply everything by x minus 4, we get that the original dividend is equal to the divisor times the quotient plus the remainder. Any questions at all? No? Okay, so that's polynomial long division. Let me give you a setup for the other kind. So if I had said, before we get to just as a setup, if we are given instructions to divide, I don't know, x to the third power, x to the fifth power minus 2x plus, say, 2x squared plus 7 divided by x to the fourth power minus x minus x plus 2. Let's say I was given the instructions to divide these two. Then remember I said you have to have every power represented in descending order, and if there's something missing you have to insert it. So when we set up our division, we have to do this. We have to insert the missing value. So I have a power of x, so I'm going to insert something in there. Well, let me get rid of this thing. I have to insert the 0 plus 0 x to the third power. And there's also missing a power of 2 plus 0 x squared. And then I have a minus x, minus x plus 2. And then that divides into, and then I have an x to the fifth power. And I'm missing an x to the third power, so I have to insert a plus 0x to the fourth power plus 0x to the third power plus 0, oh no, I already have one. And then I have a minus to the third power. And then I have a minus 2x squared. And then I have to insert the 0x plus 0x. And then I have a plus 7. So now every power is represented in descending order from the highest degree polynomial. Power 4, 3, 2, 1, no power. Power 5, 4, 3, 2, 1, no power. Okay, so then now I'm ready to move forward with long division. If you don't do this, you're going to get some weird things that happen. Any questions about that? And we can always introduce these because 0 times anything is 0. And adding 0 doesn't change the value either. So we haven't really added anything, but it helps us create the spaces we need in order for the process to work. Questions? No? Okay, so let's take a look at synthetic division. Synthetic division is a shortcut of long division that only applies when the divisor is of the form x minus c. If it fits this form, then we can use synthetic division. If it doesn't fit that form, then we can't use it, and you're going to have to do it the long way. That's a common mistake people make. They try and force synthetic division onto something that doesn't apply. So if we had, if we were asked to divide x to the third power plus 2x plus 7 divided by x minus 5, that works, right? This fits this form. The divisor is of the form x minus a constant. Or if it was x plus 2, it still fits, right? Because we can easily rewrite this as x minus a negative 2. Still fits the form. Okay? But if the original division question is x squared plus 2x minus 7, nope, there's no the synthetic division does not apply to this. Good? So it's really only applicable to cases where the divisor fits this form, x minus c. Good? Okay, so we're going to introduce this process of synthetic division. But in order to do that, let's do it with long division first, one more time to make sure we get it, and then we'll compare it to the process of synthetic division, and you can see how they compare and contrast. Okay, so we have 2x cubed minus 7x squared plus 5 divided by x minus 3. So first let's do it the long way. Long division is going to give me this. 2x to the third power minus 7x squared. And I'm missing the power of 1, so I have to insert the plus 0x to the power of 1. And then plus 5. Plus 5. Okay? Okay, so here I need to multiply it by 2x squared to make it identical to this one. That would be 2x to the power of 3. These two multiply to give me minus 6x squared. Then I distribute a negative 1 through the whole thing and add down. So distributing cancels that. If you do it right, the first term will always cancel. That's why we make them identical and then distribute a minus 1. If we distribute a minus 1, we get a plus 6. Minus 7 plus 6 gives me a minus 1, so minus x squared. Bring down the 0, plus 0x, the power of 1. Next, we make these match, so minus x will do it. Minus x times times positive x gives me minus x squared plus 3x. Distributing through by a minus 1. Oops. Distributing through by a minus 1. And then adding is going to cancel these guys. And then we get a minus 3x. Minus 3x. Bringing down that 5 now gets you a plus 5 out here. And making these match, we need a minus 3 here. Minus 3 gets you a minus 3x plus 9. Distributing through a minus 1. And then adding down. Cancels those. Minus 9 gives you a minus 4 at the end. Okay, did I do that right? Any questions, problems? Make sure that I get this thing. Okay, so that's going to be okay, I think that looks right. Okay, so this is the long way of doing it. And again, going back to the original description, we have 2x to the third power minus 7x squared plus 5 divided by x minus 3 is then equal to 2x squared minus x minus 3 plus negative 4 divided by x minus 3. And if we multiply everything by x minus 3, we get to rewrite our polynomial this way. 7x squared plus 5 equals to x minus 3 times 2x squared minus x minus 3 minus 4. Good? Good, 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 good. Okay, synthetic division, the shortcut. The shortcut is going to be to recognize that we are going to be working with just the coefficients. So let's go back to this thing. synthetic division. We have 2x cubed minus 7x squared plus 0x to the power of 1 plus 5 divided by x minus 3 in this format. So we're going to take this 3 here, and we're going to put these values like this. And we're going to write down all the coefficients in front of these powers, make sure that they're already in descending order, all of them represented. So I have to put a 2, a negative 7, a 0, and a 5. Right? These are the coefficients from here. 2, negative 7, 0, and 5. And notice that this is a subtraction of a positive number, and so we use the positive 3. Okay, so here's how the synthetic division process is going to work. We're going to bring down this 2 to begin with. What the hell? We're going to bring down this 2 right there. We're going to multiply this one times that one to give me the product, which is equal to 6 in this case. Then we're going to add down. I'm going to add these 2 down to give me, so sum, to bring me to a value of negative 1. A value of negative 1. Then we're going to multiply this guy times this guy to give me that. We multiply. This was also multiply. To give me a negative 3. Good. And then again we add down sum to give me a value of negative 3. And then we multiply this guy times this guy to give me that guy. Again, we're multiplying. And that'll give me negative 9. Negative 9. And then we add down these guys, sum, to give me a negative 4. Negative 4. Okay, the last one you get on there is going to be your remainder. Oh, I have any more colors. How about this one? Okay, so this, the last number you get on here through the synthetic division process will be your remainder. Remainder. Notice that it matches our remainder from over here. And then these other numbers, 2, negative 1, negative 3, match these numbers. 2, negative 1, and negative 3. 2, negative 1, negative 3. We have 2, negative 1, negative 3. So these are going to be the coefficients to our quotient polynomial with degrees starting with looking at the powers of the dividend here, power 3. The quotient is going to have 1 power smaller than that, always, 1 power less. So I know I start off with a 2 because this thing was a 3. If this was a 5, I'd have a 4 here. And then you have a countdown that happens. So it's going to be this plus this times x to the power of 1 plus this. And okay, well, we can just simplify it as saying it's just going to be 2x squared minus x minus 3, which is what our dividend is. I'm sorry, what our quotient is. 2x squared minus x minus 3. Good. Any questions, any questions, any questions? So we can get the same result using synthetic division. Here is what the author did to put them side by side. Here is the long version of it. This is what we did. Right? So the long version, you divide the whole thing, we end up with a minus 4. This is the same work we just did, and it looks neater. And then we have synthetic division. This whole process gets you there. Either way, we're able to get the quotient, which is these terms, the remainder, and put it all together to be able to rewrite our division in the proper format. Questions, 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 questions? No? Is that the one we did? Minus 7x squared? We already did that one. Why is this on here? Oh, okay, I guess just going through the process, which I did already. So here is the polynomial we want to divide by this. We take a 3, 3 goes out here. Get all these coefficients, 2, 7, noticing that it's missing the 0, so we have to throw in a 0 because of the x to the power of 1 term. Good, multiply, bring down the 2, 2 times 3 is a 6, add them together, they give you a minus 1, multiply these two to give you a negative 3, add them together to get a negative 3, multiply these two together to get you a 9, negative 9, add them together, we get negative 4, and that's how we get our final answer. Any questions? Okay, the next theorem shows that how synthetic division can be used to evaluate polynomials pretty easily. So if a polynomial is divided by x minus c, then the remainder of the polynomial evaluated at c, the remainder is going to be the value of p of c. What does that mean? Let's go back to this thing over here. We did, well, I put it right there. Let's go back to what I wrote. So back to here. We had this division. We had this polynomial divided by this one. We did it the long way, did a lot of work, did the long way, figured out the quotient, figured out the remainder. That means that this division is equal to the quotient plus the remainder divided by the divisor. If we multiply both sides of the equal sign by this x minus 3 part of it, right, so if we multiply this side by x minus 3, cancels with this one. If we multiply this whole side by x minus 3, it'll distribute and give me this. Good. So now I have two polynomials that are equal to each other. This polynomial is equal to this polynomial minus 4. Right? They're equivalent to each other. That equal sign is pretty powerful. So if I wanted to evaluate these, so let me make some room here. So this is saying that this polynomial, p of x, is equal to 2x to the third power minus 7x squared plus 5. But I also know that this polynomial is also equal to this polynomial product minus 4. X minus 3, 2x to the second power minus x minus 3 minus 4. So if I wanted to evaluate something, a new value, the input value x, I can either use this, which is going to be 2 times something cubed minus something times something squared plus 5, or I can use this. It's the same, they're both going to give me the same answer. Blank minus 3 times 2 times blank squared minus blank minus blank minus 3, and then the whole thing we subtract minus 4. Right? So for example, if I wanted to evaluate my polynomial, say at 2, I'd have to put a 2 there, and then I got two choices. I can put a 2 here and a 2 there. So I'd have to figure out what 2 cubed times 2 is. That's going to be 2 cubed is 8 times 2 is 16. That's going to be 16 minus 28 plus 5. And that'll give me my answer. Or I can go over here and replace all of these guys with a 2. And I would get 2 minus 3, that's going to be negative 1. Negative 1 times 4, that's going to be 8 minus 2 minus 3 minus 4. Good. So from this side, I ended up with 16 minus 28 plus 5. Which gives me negative 12 plus 5 is positive 7. Or this side tells me that this is negative 1 times 8 minus 2 minus 3 makes it minus 5. Minus 5 minus 4, which gives me positive 3. Uh-oh. Oh, this is negative? Yeah, this is negative, right? Negative 12. Yeah, that's negative 7. And then here we'll end up with the same thing. Negative 3 minus 4, which gives us negative 7. Right? So I can evaluate it this way, or I can evaluate it this way. Any questions so far on the fact that you can do it either way? Okay, so we could do it either way. That's fine. That's cute, and that's useful sometimes. But it's particularly useful when, in fact, what you want to do is evaluate it at this special number here. Let's erase all of these guys. If, in particular, you want to evaluate it at 3, say you specifically wanted to do it at 3, okay, we could do it like before. That's going to be solved by figuring out what this is. 3 to the third power is 27. That's going to be 2 times 27 minus 7 times 9 plus 5. Okay, we could keep going and find the answer there. Or notice that this makes it super easy, because if I replace all of these things by a 3, I don't know what that is, but that's definitely going to be 0. The output is going to be 0 times, who cares, minus 4, right? And it doesn't really matter what that is, because 0 times anything is 0. So this whole thing is going to be 0 minus 4. So it's super easy. The answer is minus 4. Good. And that's what that theorem is saying. Once we divide our polynomial, we can rewrite it this way. Divisor times a quotient minus the plus the remainder. And if we try and evaluate that polynomial at a 0, at this value, at c, then at x equals to at x equals to 3, then this term will become 0, and the remainder will be our answer. Good? Questions, comments, issues? Did that make sense? Anybody? Anybody? No? No questions? No questions? None? Okay. Let's go back to it. Okay, so if a polynomial p of x is divided by x minus c, then the remainder is the value p of c. So, for example, let's say we have this guy right here, 3x to the 5th power plus 5x to the 4th power minus 4x to the 3rd plus 7x plus 3. Find the quotient and remainder of the polynomial when the polynomial is divided by x plus 2. Okay, so part A is asking us to divide this thing. We have 3x to the 5th power plus 5x to the 4th power minus 4x to the 3rd power plus 7x plus 3. And we want to divide the whole thing out by x plus 2. Let's do it with synthetic division. So to do it to synthetic division, we have to have a subtraction here. So we'd have to rewrite this as x minus a negative 2, right? Because we have to have a subtraction there for synthetic division. And we have to be careful about the powers here. 4, 5, 4, 3, I'm missing the 2. So let's insert that in there. 3x to the 5th power plus 5x to the 4th power minus 4x to the 3rd power. I'm going to insert the plus 0x squared, and then I have power of 1. So plus 7x plus 3. So powers 5, 4, 3, 2, 1, 0. And then down here, it has been rewritten this way. So we're ready to go. We can do our synthetic division. And so we're going to put a minus 2 out here. And then all these coefficients. coefficient of 3, coefficient of 5, coefficient of -4, coefficient of 0, 7, and 3. Okay? So we're going to bring down the 3, multiply -2 times 3 to give me -6, add them together to give me a -1, multiply them to give me a +2, add them to give me a -2, multiply them to give me a +4, add them to give me a +4, multiply them to give me -8, 8, add them, that gives me -1, multiply them, that gives me +2, and then adding them gives me a 5. Good, so that's going to be my remainder, 5. Any questions? No? 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 I think it will help to do that. Okay, so according to synthetic division, it must mean that this little division right here is equal to, so this 3x to the 5th power plus 5x to the 4th power minus 4x to the 3rd power plus 7x plus 3 is equal to the quotient times the divisor. It's going to end up being x plus 2 times this. Now these are going to be all the coefficients of the resulting quotient polynomial starting with degree 4, because this has degree 5. So it's going to be 3x to the 4th power, minus x to the 3rd power minus 2x to the 2nd power plus 4x minus 1, and then a remainder of plus 5. Any questions about that? Good? No? Maybe? And again, that's because this is the divisor. Divisor multiplied by the quotient, and then the remainder. Did I keep track of all the signs here? Just one little mistake about a sign throws the whole thing off. So 3, -6, -1, +2, -2, +4, 4, -8, -1, +2, +5. Great. Okay, so that was the answer to part A. This polynomial divided by that, what do we get? Okay, we get this. Part B says evaluate your original polynomial at -2. What do you get? Okay, so we can divide. Let's make some room here. So part B says find your polynomial p of x, which is blank, p of x equals to, well, this whole thing here is p of x. I'm just going to write it here. P of x is exactly this, which equals that. So I'm just going to, oops, p of x equals that. So let's not repeat that whole thing. We have blank equals 3 times blank to the 5th power plus 5 times blank to the 4th power minus 4 times blank to the 3rd power plus 7 times blank plus 3. So if I want to evaluate this whole polynomial at x equals to -2, we have -2 there, -2 there, -2 there, -2 there, -2 there. Okay, doable but not fun at all, right? And that's kind of hard to figure out. -2 to the 5th power times 3, that's going to be a big number. -2 to the 4th power times 5, that's going to be a big number. So this is definitely not fun. However, we have another choice. We also know that the original polynomial is equal to this over here, the multiplication of these two polynomials plus a 5. So I can also say that p evaluated at -2 is the same thing as blank plus 2 times 3 times blank to the 4th power minus blank to the 3rd power minus 2 times blank squared plus 4 times blank minus 1 plus 5 out there. So if I wanted to find the result of our polynomial evaluated at -2, I would just have to replace all these blanks with a -2. Good. And at first you think, oh, well, this is going to be just as hard. And it's not, because who cares what this is? This is going to be a 0. We're going to end up multiplying 0. This is 0 times something. Who cares? We'll end up with 0 times who cares plus 5. And it doesn't matter what this is. The whole thing is going to be equal to 0. So I've simplified my work because I don't have to figure out what this whole thing is. It doesn't matter. The whole thing is 0 plus 5. So I know that my final answer is going to be p evaluated at -2 is equal to 5. Any questions about that? Okay, so the point is, kind of bringing it all together, that when you want to evaluate a polynomial at a value -2, you can either plug it into your polynomial and work it all out, do all that arithmetic and figure out what that is, or you can think about, even though they didn't ask you, you can think about dividing your polynomial by x minus that value you want to evaluate, use synthetic division, and then from synthetic division, the remainder will be your answer. Does that make sense? So if I said, okay, now, given this polynomial, let's say you're asked, part C now, part C, find P of 1. All right, I could plug in a 1 in all these, and that's not hard to do. 1, 1, 1, 1. Okay, that's not hard to do. Or what I could do, even though they didn't ask, I could think to myself, okay, let's divide this polynomial, 3x to the 5th power plus 5x to the 4th minus 4x to the 3rd plus 7x plus 3. Let's divide it by x minus 1 using synthetic division, which is not that hard. 1 goes into here, and then we have 3, 5, 4. There's a 0 in there. Oh, there's a minus 4. A 0, a 7, and a 3. A 7 and a 3. So use synthetic division. That's going to be 3. 3 gives me 8. 8 gives me positive 4. 4 gives me 4. 4 gives me 11. 11 gives me 14. There's my answer. My remainder. So if I wanted to figure out what this is, I can plug 1 in there, 1 in there, 1 in there, 1 in there, and figure out the answer. Or I can use synthetic division and figure out that the answer is going to be 14. Questions? No? Maybe? Sort of? Kind of? No? 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 So it's just a nice little trick or a nice little property of polynomials that helps us evaluate things a little bit in a slightly different way, and helps us to look at things in a slightly different way. Okay, so then that brings us back to the statement of before. C is a 0 of the polynomial if and only if it's true that x minus c is a factor of the polynomial. So if it factors it, that means that there is the remainder is 0. That means that this will divide into it evenly. So this goes in both directions. If you find that there is a binomial of this form, x minus c, that divides the polynomial evenly, then the remainder will be 0, and we know that it divides it evenly. And so we know that x equals to c will be a 0 of the polynomial. It means that it's an x-intercept point. Okay, so for example, here we have this polynomial, x to the 3rd minus 7x plus 6. show that p of 1 is equal to 0, use this fact to factor the polynomial completely. Okay, so because we are told that p of 1 equals to 0, this means that x minus 1 is a factor of this thing. Thus, 1 is a 0 of p of x. Because we know that's a 0 of p of x, then we also know that x minus 1 is a factor of the polynomial p of x. And now that we know that it's a factor of it, well, let's actually divide it. Let's factor it out. So let's figure out what that is. So now we have x to the third power minus 7x plus 6, and let's divide it by x minus 1. Using synthetic division, I'm going to put a 1 here, and then make sure I represent all those powers. I'll have a 1. I'm missing x squared, so I have to throw in a 0. And then x squared power of 1 is going to be a minus 7, and then a 6. Synthetic division is going to bring this to a 1, 1, 1, 1, minus 6, and 0. Just as we had suspected, the remainder is 0. And these are the coefficients of the quotient. Good. So we have established that this little fraction here is equal to x to the third power minus 7x plus 6 divided by x minus 1. And it's going to be equal to x to the second power, because it's 1 degree less than this power there. And I'm looking at the coefficients in front of here. So plus x minus 6 plus remainder of 0 divided by the divisor. And now when I multiply both sides of the equal sign by x minus 1, whole thing by x minus 1, and distribute, I'll end up with x cubed minus 7x plus 6. Oh, problems. 6 equals to x minus 1 times x squared plus 6, plus x minus 6 plus 0. So this times this cancels and we have a plus 0. So you don't have to write the plus 0 down, and we could just say that x to the third power minus 7x plus 6 equals to x minus 1 times x squared plus x minus 6, just ignoring that 0, and we've managed to further factor this thing, right? We're not totally done yet because we can still factor this a little bit more. This is just going to be something simpler to factor. We need two numbers that multiply to negative 6 but add the 1. That's just going to be 3 and 2. So this is going to be x cubed minus 7x plus 6 equals to x minus 1 times x plus 3 x minus 2. Right? This last trinomial factors into these two. Any questions? No? So simply knowing that the polynomial evaluated at 1 equals to 0 gives us a hint that this is a divisor of that. So then we can actually divide it using synthetic division, and that helps us chip away at it, right? Because if we were just told, here, factor this, and no other information is given, then that's really hard to factor, right? Because this is a power of 3, not a power of 2. Quadratic formula doesn't apply. We can't factor x out of all of these terms. They don't have an x in common. They don't have anything in common. We can't use any of our other tools for factoring. We're kind of stuck. There's no other thing we could do. But when they threw in this extra little piece of information, oh, by the way, if you evaluate it at 1, we get a 0, that automatically tells me that x minus 1 is a factor of this, so we can use synthetic division to factor it. That chips away at it. That breaks that polynomial down into a multiplication of these two. And now this is something we can easily work with. Questions, 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 questions? Right, so that's the same thing they did here. And then that breaks it into that. So that's the end of this section. Any questions? Okay, so let's keep going then. So we finished section 3.3, section 3.4 on the real zeros of a polynomial. So we're going to look at the rational zeros of a polynomial. And we're not really going to spend much time on Descartes' rule of signs or the upper or lower bound theorem. Instead, we're going to replace it with calculator work, and I think that there's sort of a blend of using technology, but also kind of keeping the spirit of the original intention of studying this stuff. Keep in mind that chapter 3, the entire chapter 3 is all about how do we graph a polynomial? How can we tell the graph, a rough sketch of the polynomial? And we've looked at end behavior, we've looked at zeros, we've looked at multiplicity. So all these things kind of help us piece it together to do a rough sketch of the polynomial. And one of those big parts is going to be to find the zeros, right? The places where it crosses the x-axis. And that's why we need to factor a polynomial so we can find all those zeros. And that's why we took that little detour about dividing polynomials and how that connects to the zeros of the polynomial. This Descartes rule of signs and upper lower bound theorems, to me, are just a bridge too far. We do have technology. We've been ignoring that this entire time, right? Maybe some of you are wondering, why are we bothering with all this work to figure out the rough sketch of a graph when we can easily just go over to Desmos, type it in, and there's the answer. So there's something to be said about that. Again, math, in my opinion, is just about studying interesting little puzzles just for the sake of studying interesting little puzzles, and that's it. It doesn't have to have a reason behind it, an application. You're never going to use it in real life. It's just a matter of doing those brain push-ups to help you become a great puzzle solver so that you can tackle real life problems, issues, puzzles, and you're really good at doing, looking for new solutions to those problems. At any rate, so there's sort of a balance between doing math just for the sake of math, just because it's fun, and also gets to a point where it's really tedious and messy, and you're like, but I have technology, I could just graph it. So that's why I'm gonna skip this Descartes rule of sign and the upper and lower bound theorems. And then graphing devices, of course, we could just use technology. So really, we're just going to focus on the rational zeros of polynomials, what that means, the theorem, and how that all applies to what we just did about dividing polynomials and finding the zeros of a polynomial. Okay, so the factor theorem tells us that finding zeros of a polynomial is really the same thing as factoring it into its linear factors. So in this section, we study the same algebraic method that helps us to find the real zeros of a polynomial and thereby factor the polynomial. Okay, so rational zeros. Remember that rational, the word rational is a fancy math word for fractional. Rational is a fractional. It's something that can be expressed as a fraction with integer coefficients. Right? Okay, so let us to help us understand the next theorem, let's consider this. So let's say we're given this polynomial, which is a multiplication of three different binomials. Right, so x minus 2, x minus 3, x plus 4. From the work we've done already, we realize that this must mean that x equals to 2 is a 0 of the polynomial, x equals to 3 is a 0 of the polynomial, and x equals to negative 4 is a 0 of the polynomial. If we went ahead and FOILed this whole thing out, we would get to this thing, this ugly thing here. And then it would be really hard, by looking at it, that the zeros are 2, 3, and negative 4. It would be really hard to find it. Off with the expanded form, we could see that there is a real value to factoring it and turning it into this, right? We also saw from just a minute ago that if we evaluate this polynomial at 2, 3, or negative 4, the output is going to be 0. And what we want to notice here is that when we expand it all, the zeros, the 2, the 3, and the negative 4, are all uh, are all divisors of 24. Okay, good. Okay, so again, not that there's any proof of this given to you. This is, again, one of those things in math where proving it would just take way too much. So we're just not going to prove it. This is one of those things you're just being asked to understand without really proving where it came from. And even just that part is a little confusing. So that's all we need to know. Okay, so this theorem says that if we have a polynomial, a standard polynomial degree n, just like we've been working with, here, this guy right here, what we're going to do is look at the constant at the end. That's going to be this a sub 0. We're going to look at the constant in the front, the a sub n, right? The leading constant in the leading term, and the leading coefficient in the leading term, and the constant at the end. Those two are going to be what we need in order to create a list of possible rational zeros for this polynomial. Good. So any number of this form, any rational number that is a zero of this polynomial will be of the form p over q, where p is a factor or a divisor of the constant at the end, and q is a factor or a divisor of the coefficient in the front of the polynomial. I know that must sound a little confusing, so let's just jump right into what that means in terms of an example, and we'll come back to this definition. So let's say that I want to figure out all the zeros of this polynomial. The zeros of this polynomial, according to that theorem, are going to be values that are in this list. You know, and I don't like that it... Okay, that's fine. We'll do another one next. But okay, so the value in front, since there's no number, by default, that means that there's a little 1 there, right? So that means that this is the a sub n. Well, in this case, it's a sub 3. And then this guy is the a sub naught. Okay. All right, so we're going to look at all the divisors of 2. Well, factors. Well, there's just 1 and 2. And 1, well, that's just 1. So this one's such an easy one, it might be kind of confusing. But, okay, so this theorem says that anything that's a zero of this, any rational zero will be in the list, right? So we create a list of suspects, and the suspects are going to be all the divisors of the constant at the end divided by all the divisors in the front. So it's every possible combination of plus or minus 1, plus or minus 2, divided by plus or minus 1. Right? So since it's just a 1, it really just ends up being any plus or minus 1, comma, any plus or minus 2. Which means it's just the numbers -1, -2. Oops, let's put them in order. -2, -1, +1, +2. According to this theorem, any zeros that exist that are rational zeros, right? So the only thing that would be left is irrational zeros. So this does not account irrational zeros. So any rational zero, any number that can be expressed in the form p over q, where p over q are any integers, is going to be in this list. And we only have these ones to deal with. So as I try and figure out the zeros, rational zeros, I only have to test these points. I know for a fact that p of 3 isn't going to work out because 3 is not on this list. P of 1/2 is not going to work out because it's not on this list. Does that make sense? Sort of, kind of, maybe. Okay, so now once we have the plus or minus 1, the plus or minus 2, all we have to do is test those values, right? So 1 was on the list, so we try 1. 1 cubed minus 3 times 1 plus 2, that's a 0. We try negative 1. Negative 1 to the power of 3, okay, so that doesn't give me a 0. So this fails to be a 0. Right? Just because it's on the list doesn't mean it's an actual 0. So we have to test them. We keep going. Try a 2. 2's on the list. Nope, that doesn't work either. So that one is not a 0. We can eliminate that one. And then negative 2. Negative 2, we put in there. Oh yeah, we found it. So we found that the rational zeros are 1 and negative 2. Good. From that, we conclude that this thing must factor. That must mean that when we look at 1 and negative 2, that must mean that 1 and negative 2 are zeros of p of x, because p of 1 equals to 0 and p of negative 2 equals to 0. So it must mean that x minus 1 divides p of x, is a divisor, we say factors. Factors p of x. And therefore I know that x minus negative 2, which is otherwise known as x plus 2, factors p of x. Good. So I know two polynomials that will divide into this evenly, and that will help me figure out how to factor the whole thing. Good. Once I know that these two are divisors of that, then I can use synthetic division to actually divide them. And it just simplifies my life. Right? If I want to find the factorization of all this, you're kind of left without anything to do. Like, I don't know, how do you divide this whole thing? How do you factor it? Well, according to this process, if you find zeros through this theorem, then once we find at least 1 0, it gives me something I can divide it by and break it down. Good? Any questions about that? No? No? Maybe? Okay, so here's our strategy for finding the zeros of a polynomial. Okay, we're going to first of all look at our expanded polynomial. We're going to create the list of possible zeros, and that underline possible. That doesn't mean every number on this list is going to be a 0, or really even any number on the list. But I do know that if it's not on the list, then and it's a rational number, then it definitely cannot be a 0 of the polynomial. So create your list of possible rational zeros. From that list, you're going to use synthetic. You're going to figure out which ones are the ones that evaluates to produce a 0. We're going to use technology on that part to figure out which ones are the zeros. Once we find the zeros, then that's a really big hint to let us know which binomials of the form x minus c, or c is a rational zero on the a rational value on the list, which binomials divide our polynomial. We can divide them and then begin to chip away at our polynomial that way until we find its full factorization. Questions? Okay, here's another example. So let's say that they ask us to factor this polynomial. That is really, really ugly. We would initially try maybe factor by grouping, right? Before this whole chapter, the first thing I would try and do is factor by grouping, see if that works. So factor by grouping would be this. Let's put 2x to the third power plus x squared minus 13x plus 6. So first I would focus on the first two terms, see what they have in common, and they have an x squared in common. Factor that out, leaving me with a 2x plus 1. And then, oh, wait a minute, there's no way to factor out something from these last two terms such that we end up with a 2x plus 1. So factor by grouping is going to fail, right? It's just not going to give me any useful results. Is that okay? Does that make sense? Is that clear? Okay, so prior to this chapter, at this point, we'd be stuck. I don't know how to factor this. It's ugly. They don't have any other terms in common. I can't use the quadratic formula because this is power of 3. You're kind of stuck. And so this gives us another possible way to proceed. So step number 1, create the list. Step number 1, it's going to be create list of possible zeros. Okay, so it's going to be all the divisors of the 6. So it's going to be the list, P over Q, is going to be this list that has divisors of 6 divided by divisors of 2. Okay, so all the things that divide 6, it's going to be plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. Right? Those are all the divisors of 6, divided by all the divisors of 2, which is going to be plus or minus 1 and plus or minus 2. So here's my list. It's pretty big. Okay, so it's going to be 1 divides all of these to give us those values. So it'll be plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. And then all of these divided by 2, and you don't have to repeat. So I'll get 1 over 2, so I get plus or minus a half. And then 2 over 2 is a 1, and I already have 1, so I don't have to repeat that. And then plus or minus 3 over 2, plus or minus 3 over 2, comma. And then plus or minus 6 over 2, which is a 3, and I already have a 3, so I don't have to repeat that again. So I'm done. Here's my list. Okay, so I've created a list of possible rational zeros. Of all the rational zeros that exist, the ones that are zeros must be on this list. Now there might be none. Maybe there is no such thing as a rational zero to this thing. Maybe that's possible. So I have to test each of these. But it limits down our world from any real number ever, any rational number ever, down to just this list of 1, 2, 3, 4, 5, 6, and then the plus and minus. So there's 12 things to check. If I check these 12 things, I'll be good to go. I'll be able to tell. I can tell that 7 is not a rational zero because it's not on the list. I can tell that 24 is not a rational zero because it's not on the list. Does that make sense? Okay, so the next step is the step where we're going to kind of use technology instead. So the book tells you to check each one of those values, but we're not going to do that. Does this already have the answer? Okay. So the next step would be to evaluate each of these values at each of those zeros. So step 2 would be to check this equals to 2 times blank to the 3rd power plus blank plus blank squared minus 13 times blank plus 6. So we have that right there, and they want you to figure out each of these. Figure out what happens when you plug in a negative 1. Negative 1, negative 1, negative 1. Okay, and when we plug in negative 1, what we're looking for is to figure out, does this equal 0, question mark. If it equals to 0, we found the 0 of the polynomial. If it doesn't equal 0, then it doesn't really matter what it is. We don't even really care what the number is. We just want to know, does it equal 0? Once we check negative 1, we're going to check the other ones. What about positive 1? Positive 1, positive 1, positive 1, positive 1. Does that equal 0? If it does, great, we found a 0. If not, then we move on. Then we check the other ones. Right? So it's kind of a meticulous checking of all of these. How about negative 2? Negative 2, negative 2, negative 2. Does that give me 0? Okay, so you can do that by hand and check all 12 of them. It's not the end of the world. But instead what we're going to do is we're going to use technology to do that. It makes it a little easier. And to do that, let's take out our calculators. So let's go over to our TI-84, and there's a nice little shortcut function that will be useful. Oh. Okay, the first thing we want to do is come up here to y equals and get rid of this thing, and we're going to type in our polynomial. So we have 2 times parentheses, and I just like to wrap up everything in parentheses, x to the power of 3. It's really extra unnecessary in this format because it lets me write the power of 3. But for many of you, it does this little caret symbol, a little caret symbol that looks like this one, and then the 3, which makes it a little confusing. So if you have that kind of calculator, I would recommend that you wrap it up in parentheses to make sure that you're typing in what you expect to type in. Otherwise, if you have the newer ones like this one, then it makes it clear that you have an x squared minus 13x plus 6. Okay. Now, let's say, for example, 1. 1 is really easy. If we try typing in 1, let's go back over here for a second and let's type in a 1. Let's do the easy ones. I like doing easy ones. When we try putting in a 1 there, 1, 1, 1, 1, then this is pretty easy. That's just going to be 1, so that's just going to be 2, plus 1 minus 13 plus 6. So that's going to be 3 minus 13. That's negative 10 plus 4 equals to negative 4. Right? So at 1, I get a negative 4. Okay, back to our calculator. There we go. Okay, so next we're going to go over to this little button that says table, table set. It's right above the window, right? But it's written above the button. So we first have to hit this second button. This little up arrow will start blinking. That lets me know that the writing in blue is what takes effect when you hit that button. So now I hit this button and it'll do table set. Okay, so table set gets you to this menu. Now you're going to go down to where it says independent variable, and you're going to move it over to where it says ask, and then hit enter. Okay, if it's already like that, then that's fine, leave it alone. But I want the independent variable to be under ask, not auto. Good. Again, you hit second, table set. That gets you to this menu. Use your arrows down. Go over to where it says ask. Enter. Good. Next, we're going to go over to where it says table. Right above the button that says graph in the upper right-hand corner, table. Again, it's written in blue. So I'm going to hit second and then this. And that gets me to this table format. Okay. Y sub 1 is the equation that I typed in. Notice that if I go to y equals, y sub 1 is exactly this polynomial that I typed into my calculator. So I'm going to go to table like this. And now what happens here is that if I type in a value, like say 1, and enter, it'll automatically evaluate that polynomial at that value. So see how I put in a 1 here and cubed it and this and that and the other. I did all this work and I got a negative 4. Well, that's where this negative 4 comes from. It makes it easy. And if I type in a 0, well, that one's really easy too. Because if I put this as a 0, 0, and a 0, the answer is just going to be 6. Good. So this makes it an easy way for me to evaluate my polynomial at any number I want. And in particular, what I want to do is evaluate it at all of these numbers right in here. At all of these numbers right in here. Good. And what I'm looking for is for a number that outputs a 0. That'll be a 0 of the polynomial. So I've already tried 1. Let's try 2. Ah, look, 2 is a 0. I found one. going back to over here, I have that p of 2 is 0. So 2 is a 0 of my polynomial. Good? Questions, 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 questions? Okay, I got to keep going. Let's find them all. Okay, so let's check them all. 2 worked. How about 3? No, 3 doesn't work. 3 gives me 30. 6? Nope, that doesn't work. So I've tried 1, 2, 3, and 6. Now I have to find their negatives, or try their negatives. Oops, how about 1/2? So 1/2, which is the same thing as 0.5. Ah, 0.5 also worked. So I found another 0. And also 3 over 2, which is 1.5. 1.5. No, that one didn't work. Okay, now I have to find, try all the negative ones. How about -1? No, that didn't work. -2. No, that didn't work. -3. Yes, -3 worked. -6. No, that didn't work. -0.5. 0.5. Nope, that didn't work. And -1.5. Nope, that didn't work either. Good, good, good. Okay, so looks like 2 is a 0. We found that one. And so is positive 1/2. That's a 0. And so is -3. -3 was a 0. And p of 1/2 is a 0. Okay, so we found 3 zeros of this polynomial. Good. Questions, 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 questions? Because they're zeros, that must mean, right, the definition of what this means, the result of what this means. So from here, that must mean that, so x minus 1/2 divides p of x. Like that over there. P of x. It must mean that x minus a -3, otherwise known as x plus 3, also divides p of x. And from here we know that that must mean that x minus 2 divides p of x. Good. Questions, questions, questions? In the next section, there's a theorem that lets us know that this guy right here gives us a clue as to how many there's going to be. There's 3 here, there's 3 there, so there's a connection there. There is a little more complication to that, and we're not going to cover the next section, so we're not going to talk about that. But in this case, it just so happens that the actual polynomial then equals to all 3 of these. P of x, which is equal to 2x to the 3rd power plus x to the 2nd minus 13x plus 6. Because I know that I was looking for 3 of them and I found 3 of them, it must mean that this whole thing equals to x plus 3, x minus 2 times x minus 1/2. But okay, so another thing we would do though, if it doesn't always work out that the zeros are gonna have the exact same number as that, and that we have, and that means that we have that many factors. So for example, if this thing was 5, and then we do our work, maybe we only find 3 of them. That means that there's more out there missing, right? It's not complete yet. So in order to figure out how to factor it, then we would use synthetic division to actually go ahead, move forward, and factor the whole thing out. Good. Questions? Questions, questions, questions? No? 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 Okay, so this is what the author did, right? So they create that list of possible rational zeros, just like we did. So here's that list. Simplifies to this list. And now we start checking each of these things. Once we find the ones that work, so we found that 2 was a divisor, then we can use synthetic division to actually divide it. Right? So here they use synthetic division with the number 2. And for us, we don't have to bother with this. See, the author skipped the part about the calculator, so they don't really know which ones work and which ones don't work. So they're kind of blindly going through all the synthetic divisions until they find the remainders of 0. Right? So we save ourselves a little bit of work. We automatically know this is going to fail because we know that P of 1 from our calculator is not 0. Right? From our calculator. So it saves us this work. We don't have to do this work. But because P of 2 did equal to 0 from our calculator, then I know that x minus 2 is a divisor of the P of x. So then when we do our synthetic division, I know the remainder will be 0, which means that this is the resulting quotient polynomial. Good. And then I can break that down a little bit more. I started out with this polynomial, and now I know that x minus 2 is a divisor, and these coefficients, 2, 5, and minus 3, come from here. See how I managed to start to factor it down. Now at this point, this one's a nice quadratic, so maybe you can actually factor it, guess and check your way through it and factor it. Or we can break it down this way. You know what? See, this reminds me, when I went up here, I made a mistake, and that's because I skipped a section. When I said that this equals to this, I forgot to mention that it equals to a family of polynomials where there is a potential constant out in front of here to make it equal. So there's a constant to be determined to give us exactly that. And so when we factor it this way, we see that if we had written it in terms of a half, so this could be thought of as x minus 1/2, and so it's missing a 2. So I could say that if I factor out a 2 out here, 2, and it's x minus 2, x minus 1/2, x plus a 3. Okay? And so this 2, when we distribute, we get this guy. And now it fits the exact same form that I wrote up here. Blank, and then we have these terms here. Any questions? No? No? So this whole section will be all about factoring really ugly things. And your plan of attack is going to be, look at the expanded polynomial, right? You're going to look at, you're going to create, the first thing you do is you're going to create a list of possible rational zeros, which will be a fraction where the numerator is all the divisors of the constant at the end. The denominator will be a list of all the divisors of the leading constant in the front. Figure out all those possible combinations, plus or minus. Create the function in your calculator. Test them all out. The ones that are zeros are factors of your polynomial. So then you'd have to use synthetic division to begin to chip away at it and factor the whole thing out. Good. Only in the case where it so happens that you find a unique number of zeros which matches the power of the polynomial, only in that case can you write it, write it all out as a product of each of those zeros times a constant. If it doesn't match that power, then it's a little more complicated. So the only way to do it is to actually use synthetic division. Questions? All right, let's look at the assignment in 3.4, and maybe we'll grab one and do one more example. So let's go over here. That's not what I want. This one. All right, 3.4. Functions. Chapter 2. Remainder theorem. Okay, we're on the right track. This is 3.3. 3.4. Okay, remember, your book talks about all these upper and lower bounds and the Descartes rule assigned, all the things. Don't worry about any of that. Doing it my way is just as good and kind of drives the point. Okay, so we're going to use this whole thing to factor ugly polynomials. So let's just jump into a really ugly polynomial. Find the zeros of the polynomial, use the quadratic formula if necessary. Okay, so I don't know, let's just grab one that has some ugly numbers in the front and the back. Well, these are all too easy. They were pretty nice to you because they have a 1 out in front for most of these cases, or a number that doesn't have too many divisors like this 3. If it was a little more, if they wanted to be a little more cruel, they'd give you some constants that have a lot of divisors, like a 24. Right? A lot of numbers divide into 24. So I don't know. Okay, look, like 24 right here. This was an ugly one. Let's do this one. Oops, whatever. Okay, so 37. Let's try number 37. So we want to find all the zeros of this polynomial, factor the whole thing out, number 37. Let's move that away, and let's get back to you. And I need space. So number 37 is p of x equals to 24x to the third power plus 10x to the second power minus 13x minus 6. Okay, so the first thing we want to do is come up with a list of possible rational zeros, right? Let's do that. So list of possible rational zeros would be of the form p over q, which is the divisors of 6 divided by divisors of 24. That's going to be plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6 divided by plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, plus or minus 8, plus or minus 12, plus or minus 24. Ooh, so this one's going to be a real fun one. Lots of different possible combinations. Okay, so the 1 going into all of those, of course, is just going to give me plus or minus. Okay, so instead of copying plus or minus all over the place, I'm just going to put it on the outside. Plus or minus 1, 2, 3, or 6. That's what happens when I divide all of these by a 1. And then divide all of those by a 2, I'll end up with a half, or a 1, which I already have, or a 3 over 2, or a 6 over 2, which is a 3, I already have that. Then I'll have a 1/3, a 2/3, then a 3 over 3, which I already have, and then a 3 over 2, which is 2, I already have that one. Okay, then 4, I'll have a 1/4. 2 over 4 is a half, I already have a half. 3 over 4 is a new one. And then 6 over 4 is 3 over 2, which I already have. So it took care of the 4. Then there's 6, so it's going to be 1 over 6, comma. And then 2 over 6 is 1/3, which I already have. And then 3 over 6 is a half, and I already have that. And then 6 over 6 is 1, and I already have that. Okay, then I have 1/8. Then 2 over 8 is 1/4, I already have that. And then 3 over 8, that's a new one. And then 6 over 8 is 3/4, I already have that one. Then 1 over 12. 2 over 12 is 1/6, which we already have. 3 over 12 is 1/4, which we already have. And then 6 over 12 is a half. We already have that. Good. Next will be 1 over 24. 2 over 24 is 1 over 12. We already have that. 3 over 24 is 1/8. We already have that. And then 6 over 24 is 1/4, and we already have that. Okay, so we're done. This is the list. Pretty ugly, but really there's only 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and then plus or minus, there's 30 numbers to check. 30 numbers to check. This is where the book would have you actually do them all. So you'd have synthetic division for the case of x equals to 1, see if the remainder is 0. Synthetic division for the case x equals to 2, see if the remainder is 0. Right, so you do a lot of guessing and checking with these values, and you're going to get a lot of wrong things. So as a way of saving time, we can turn over to our technology and use our technology to test these values so we can identify which ones are the ones that are going to work. So go over to y equals and type in the equation 24x to the third power, x to the third power, 24x to the third power plus 10 x to the second power. Oh, it's just moving it? Okay, that's fine. Minus 13x minus 6, and then I have to delete all of this stuff. Delete. Oh man, it's not working out. Delete. Come on. You're annoying. Okay, so I should have cleared the whole thing out first and then hit delete. Okay. 24x to the third power plus 10x squared minus 13x minus 6. Good, so we have our polynomial. Again, we're going to go over to table, and we've already done the table set once, so we don't have to do it again. So let's hit graph, table graph, so we get to this. And now I'm going to delete all these input values, because I don't need all of those values, I need new values. Okay, and I'm just going to start going through until I find at least one value that works. So I'm going to try a 1. I'm going to try a 1. That didn't work. How about a 2? That didn't work. How about a 3? That didn't work. How about a 6? That's not working. How about a 0.5? Nope. How about a 1.5? Nope. How about a 1/3? So 1 divided by 3. No, that didn't work. How about a 2 divided by 3? Nope, that didn't work. 1 divided by 3 divided by 4? Nope. How about a 0.75? Ah, found one. Got it. 0.75 is a winner. That would be this guy. Okay, so we have 1. How about a 1/6? 1 divided by 6? Nope. How about a 1 divided by 8? Nope. How about a 3 divided by 8? Nope. How about a 1 divided by 12? Nope. How about a 1 divided by 24? Nope. Okay, how about negatives? How about -1? negative 2, negative 3, negative 6. What? Negative 6. Oh, negative 0.5. Ah, we found one. Another one right there. And my calculator is annoying because then it's not scrolling down to add more values in my table. So I'm just going to stop there for now and come back to this. So we know that 0.75 and negative 1/2 worked, right? This one worked. P of 3/4 was 0. And then negative 1/2, which comes from this plus or minus here, plus or minus. P of negative 1/2 was also a 0. Okay, so I know for a fact that x minus negative 1/2 will be a divisor of my polynomial, otherwise known as x plus 1/2. And I also know from here that x minus 3/4 will also be a divisor of my polynomial. If I keep going and find one more, I will be almost done. I can rewrite it in the form of a constant times these two. Well, there's one more missing, so times the other one. So let's keep going through it and find the other one. So I'm at negative 1/2. So let me scroll up here. I've tried negative 1/2. How about negative 1.5? Negative 1.5. Nope. Negative 1 divided by 3. Negative 2/3. Negative 2 divided by 3. Yep, we found it. Negative 2/3. Okay, going back over here. Probability, not probability, the polynomial valued at negative 3 divided by 2 is also equal to 0, which means that x minus negative 3, 2, otherwise known as x plus 3 divided by 2, is a 0, a divisor of my polynomial. At this point, I can conclude that p of x equal to 24x to the third power plus 10x to the second power minus 13x minus 6 is equal to some constant, to be determined, some constant that goes there, times x plus 1/2 times x minus 3/4 times x plus 3/2. Okay, so I can put whatever constant I want into here. So there's like a whole family of possible answers with a constant out in there. So if I want to get rid of all these fractions, though, then I want to introduce a value that all of these fractions can divide into. It seems like 4 would be a great choice. So let's let a 4 go into there. And then when I distribute, well, that's not true. I don't want a 4. I want to distribute a 2 into here, a 4 into here, and a 2 into there. So it's really a product of all of those that I really want to do. So I want to do 2 times 4 times 2, which is really 16. Right? So let's make a equal to 16. X plus 1/2, x minus 3/4, x plus 3/2. And then when I distribute, remember with multiplication, I would distribute to one of them, not to all three of them. So I want to distribute this 2 into this binomial. I want to distribute this 4 into this binomial. And then I want to distribute this 2 into this binomial. And then I would end up with 2x plus 1, parentheses, times 4x minus 3 times 2x x plus 3. And there is my factorization of this polynomial. Any questions? Again, this was another kind of coincidence that we had a polynomial given that has a degree 3, and we found 3 unique zeros. That's why I was able to do this. If we didn't find 3 unique zeros, or if you just want to do it in a slightly different way, then what happens is that as soon as you find one of the zeros, as soon as we find out that x plus 2, for example, x plus 1/2 is a divisor, then what you would do is use synthetic division to move forward and chip away at this and continue the factorization, right? So, or if after we find that x plus 1/2 is a divisor, then what we could do is actually divide it, use synthetic division. We end up with negative 1/2 out here, and then we have to divide this whole 24, 10, minus 13, and a minus 6. Powers of 3, 2, 1, 0, so all the powers are represented. And remember that this has to be of the form x minus a negative 1/2, so that's why we have a minus out here. And then we use synthetic division. That's going to be 24 times negative 1/2, that's going to be negative 12. Add them together, that gets me negative 2. Times negative 1/2, that gives me positive 1. Add them together, we get negative 12. Multiply them together, we get positive 6. And then we get that 0 that we expected, right? 0 remainder. That's why this is a divisor of that. So from here, we've established that our polynomial, p of x equal to 24x to the third power plus 10x squared minus 13x minus 6 is really equal to x plus 1/2 times, and then this is the resulting quadratic with these coefficients, 24x squared minus 2x minus 12. And from here, since it's a nice quadratic, we can use guess and check methods to simplify this and figure out how to factor this guy. Or we can keep going. Now, once we keep going through this guy, we also found out that negative 3 over 2 is a 0 of this, which means that x plus 3 over 2 is a divisor. We also found out this one. Minus 3/4 is also a positive 3/4 is a 0, therefore x minus 3/4 is a divisor. So now if p of 3/4 equals 0, that means that x minus 3/4 divides p of x. But also, it must mean that 3/4, so x minus 3/4 must also divide this. 24x squared minus 2x minus 12. Why is that? Consider this. Let's say I have 80, and I told you that 2 divides 80, 4 divides 80, 8 divides 80, right? These are all the divisors of 80. Okay, so then if I break this up, I actually use the 2, then that means that 80 equals to 2 times 40, but also 5 was a factor of this thing, right? So then 5 divides 80, so it must also divide the 40. So I can continue to break this up and say, well, 5 was a divisor of the 80, so therefore it must be a divisor of the 40 because 2 times 40 is equal to 80, right? And 5 certainly doesn't divide 2. Okay, so that must mean that this divides this, so we can use synthetic division on it. 24, negative 2, negative 12. And then I have this 3/4. So 24 times 3/4. So divided by 24 divided by 4 is equal to 6 times 3 is going to be 18. Add them down, we get to 16. 16 divided by 4 is 4 times 3 is 12. So we get the 12, and then that gets us to our remainder of 0. So from here, I can tell that our polynomial has been further broken down into the following. P of x is now equal to x plus 1/2 times x minus 3/4. And here are my remainders. 24x plus 16. Good. I can simplify this now. I mean, I'm kind of done, but then there's different ways to simplify it. So I can factor out an 8 from here, and I get an 8 out here, and then I'll get a 3x plus 2 in here, and then I'll have an x plus 1/2, and then x minus 3/4. And then I can break this 8 down into a 2, 4 times 2, x plus 1/2, and then an x minus 3/4, and then a 3x plus 2. I can distribute this 2 into the first binomial, and this 4 into the second binomial, and we arrive at our factorized form that looks like this: 2x plus 1 times 4x minus 3 times 3x plus 2. Questions? 4x minus 3 and 2x plus. Wait, does it match? Something's wrong. Where did I make a mistake? Why do I have 3x plus 2 and I have 2x plus 2 there? 4 minus 3, 2, 3x plus 3, 3 over 2. 3 over 2 is a 0. Is this right, that negative 3 over 2 was a 0? So then I need to multiply by 2 and it gives me a 3. So from here I can tell the zeros are, something is weird, right? So the zeros are negative 1/2. Negative 1/2 will give me negative 1 plus 1 is 0, so that's one of the zeros. Here it's going to be positive 3/4 is a 0. And here negative 2/3 is a 0. Negative 2/3. Why did I say that negative? Let's look at our calculator to confirm the results. Something is missing here. Let's confirm these. Negative 2/3 is a 0. Negative 2/3 from here. Negative 2/3. Negative 2/3. Oh, okay, so this was wrong. I don't know why I put that there. Negative 2/3, not negative 3/2. You guys didn't correct me. I blame you guys. So this thing is wrong right here. It's negative 2/3 that was the 0. Negative 2/3. 2/3. 2/3 was the 0. Not this one. This one's not a 0. So we had negative 1/2 was a 0. We had p of 3/4 was a 0. And negative 2/3 was a 0. So going back over here to expand this out, then negative 1/2 was a 0. Positive 3/4 was a 0. And negative, so this should have been, so this thing is wrong, which means this thing is wrong, which means this whole thing is wrong. So let me just rewrite it again. So this should have been some constant, x plus 1/2 times x minus 3/4 times x plus 2/3. Not 3/2, it's going to be the other way around. I flipped it around, right? And it's plus because the negative, when you input x by this value, you're going to get a 0. So negative 2/3 is going to give you a 0. Good. And now the constant that would work is going to be something that involves multiplying a 2 into the first binomial, a 4 into the second binomial, and then a 3 into the final binomial. And so from here, so that means that this constant would be equal to 12 times 2 is 24. 24 times these three, x plus 1/2 times x minus 3/4 times x plus 2/3 is equal to your original binomial. And then if we distribute and simplify it, we'll end up with a 2 distributing into there. We get 2x plus 1 for the first binomial when we multiply 2 times this first binomial. 4 times this middle binomial will give us 4x minus 3. And then 3 times this last binomial ends up giving me 3x plus 2. Good. And now that one matches this one. Right, this one now matches that one. Okay, sorry about that. Any questions? You still with me, or did that confuse people? Silence means you are following, you assume? Okay, I would guess that maybe a few of you are a little confused and need some more help with this. So tomorrow we'll go back to look at these problems here from the book and pick another one. In particular, I would like to pick one that doesn't have these guys. In particular, I'd like to pick one where the number of zeros doesn't match the degree of the polynomial. So far, every case we've looked at, both cases we've looked at, it had the degree 3, and then we found 3 unique zeros. So we'll try another one, maybe like this one has degree 5, and we might not find 5 unique zeros, rational zeros. So in those cases, we're not going to be able to jump to the conclusion of what the product of binomials is going to be. In those cases, we actually have to do a synthetic division to break it down and figure out the factored form, or break it down as much as we can by using synthetic division. Okay, so this would be a good place to stop then.